this is practice set 10. Okay, so let's get on it. So here it says Ali and Kiana bury treasure together in their school's field. The field is 400 feet wide. 400 feet wide. So the field, and let me write this. It's 400 feet wide. The actual field. Right. Ali made a map, so she took that field in real life, and in her map, in her notebook or her sketchbook, she made a drawing of that, and she made it in 8 inches. So she represented the 400 feet with 8 inches. What is a scale? Right, well, let's start with the scale. Well, the scale, well, it's given to us. She says she's going to use 8 inches, and she's going to use that to represent 400 feet there. And it's asking you for 2 other possible scales that Ali could have used to make this map. So one of them, well, let's simplify this. If I divide top and bottom by 8, I'm going to get 1 inch. And 400 divided by 8 is 50 feet. So she could have used that scale too, right? Notice that this guy here and this guy here is exactly the same thing, just written in a different manner. What's another way of representing 1 inch, 50 feet, or 8 inch, 240 feet? Well, she can have written, well, instead of dividing by 8, what if she divided by 4? Right, so 8 divided by 4, it's 2 inches. And the bottom divided by 4, 400 divided by 4 is 100 inches. So she could have 400 feet, sorry. So she could have also written it this way. So three different versions, right? 3 equivalent ratios, each saying exactly the same thing. Okay. So now Kiana made her own map. So Kiana here has, and her scale is 1 inch. All right, so this is Ali, by the way. Right, Ali over here. So Kiana has her own scale. And she says, no, I'm not going to use that. I'm going to use 1 inch is 20 feet. Right, let's focus here. Let's compare these two because these two are in unit rate. So Ali said 1 inch is 50 feet. Kiana says 1 inch for me is going to be 20 feet. So whose drawing is going to be larger? Ali or Kiana? So remember when we talked about in class when we were comparing, think about this. Right, that's 400 feet. Let's do Ali. So if you do Ali, every 1 inch, 50 feet, 50, so I'm going to write 0, 50, 100, 150, 200, 250, 300, 350, 400. There. That's using Ali, right? Where every 50, 50, 50, 50, 50, 50, 50, 50. Every inch is 50, right? Until you get to 400, so that's Ali. Now, Kiana say, no, every inch is going to be 20. So I'm just going to write Kiana over here. So that for her, the same inch, but instead of 50, this is 20. 20. Another 20. So that's 60, 80, 100, 120, 140, 160, 180, 200, 220, 240, 260, 280, 300, 320, 340, 360, 380, 300. So which scale gave you the longer representation here? Kiana, right? Why is that? Well, because 1 inch for her is 20 feet. So there's less, right, of the actual distance in 1 inch in Kiana than in Ali. In Ali, she fit, in every inch that she used, she fit actually 50 feet. So you get to use less, right, to represent the full one. So which one is larger? It's going to definitely be Ali. I'm sorry, larger. Which map is going to be larger? I apologize. It's going to be Kiana. So notice that Kiana is much, much longer, right? Her presentation, her drawing is going to be much larger. Okay, on Kiana's map, all right, so let's keep going. On Kiana's map, the treasure is 2 inches from the south edge of the field. How far is the treasure from the south edge on Ali's map? So using Kiana's map, all right, let's figure out what 2 inches is. So 1 inch is 20 feet. What if you have 2 inches? How many feet would that be? Well, this one's kind of easy, right? So we can just, hey, multiply by 2. The bottom I multiply by 2, I get 40 feet. So the actual distance is 40 feet. And we want to go back, and this is where it gets a little confusing. So now this is in Kiana's map, right? So now we're going, so this is Kiana's map. 2 inches is 40 feet, but what about in, how far is the treasure from the south edge on Allie's map? So we're going to, on Allie's map, so let's go to Allie, and we're going to use the scale in Allie's 1 inch. We're going to use the simplified version, 50 feet. And we want to know what 40 feet is in Allie's map. So we have 40 feet over here. How many inches would that be? Cross multiply, we have 50x equals 40, divide by 50, divide by 50. X is going to be 0.8 of an inch, not even a full inch, 0.8 of an inch. For on Kiana's map, okay, the area of the field is 16 inches square. Ugh, okay, this one's a tough question. So, let's see if I can do this correctly. On Kiana's map, the area of the field is 16 inches square. So, 16 square inches. So, let's think about what a square inch looks like. This is a square inch, where this size is 1 inch, and this size is 1 inch. And if I asked you to find the area of this, the area will be 1 square inch, right? Because you multiply side times side. 1 square inch. And there are 16 of these. So there are 16 of these. So imagine a figure, a shape, right? And inside 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 1 square inches on Kiana's map. The area of the field is 16 of these. And not necessarily in this shape. You could actually do it this way. I still have 16 over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whatever shape it is, okay, I have 16 of these 1 square inches. Now, here comes the tough part to explain. Let's change that into using the scale on Kiana's map. Okay, so we'll just go up a bit. I forgot the scale on Kiana's map. It's 1 to 20. Okay, so on Kiana's map, right? So let's take that same. Instead of 1 inch, right? In Kiana's map, 1 inch would actually be 1 foot, right? And actually, 1 inch on Kiana's map. I apologize. Make this a little better. So, using the scale, this scale right here, on Kiana's map, if I took that square inch, every inch would actually translate to 20 feet. So this would be 20, and this would be 20. So I'm changing the 1 inch squares into 20 feet square because that's the scale. So every inch represents 20. So in real life, that inch there would be 20 feet, and this would be 20 feet. And if you multiply these two, you get the area, which is 400 square feet. Just keep it consistent. Square feet. Now, how many of these 400 square feet do we have? We have 16 of them, right? Because there were 16 of these, so I changed. So you change one of these, right? 1 inch by 1 inch to 20 feet by 20 feet, because that's a scale. And then you find the area of one of these, which is 400 square feet, and then you multiply by 16. So 400 times 16. You get 6,400. And obviously, this is not the right answer. gives you 6,400 square feet. 5. Yeah, fine. So this is where we want to find equivalent ratios, right? In this case, equivalent scales. Let's look at the main scale. It says 3 centimeters to 15 meters. I'm going to change that to a unit scale. So instead of 3 centimeters, I'm thinking in terms of 1 centimeter. Divided by 3, I can think of this as 1 centimeter is 5 meters. It means the same exact thing, it's just written in the unit right? Where we're comparing it to 1 centimeter. So it makes it much easier. Let's look at A. Why would they do this? Select all scales that are equivalent to centimeters to meters. Now, look at first one says 3 inches to 15 inches. Anybody see a problem with this? Raise your hand if you see a problem with that from the get-go. Why would they do this? It's beyond me. Well, one is in centimeter, the other one is in inches. They can't. No, I don't believe they actually want this. First of all, we would have to change his inches to centimeters. I'm gonna use Alexa. Alexa, what's 1 inch in centimeter?
1 inch is 2.54 centimeters.
Right, because this is comparing centimeters to meters. This is comparing inches to inches. First of all, we have to have the same units. So 3 inches, well, every inch is 2.5 centimeters. So let's change that to multiply that by 3. So we get 12, carry 1, 16, 7.62. So 3 inches is the same thing, approximately 7.62 centimeters. And then let's multiply 15 times 2.54. 2.54 times 15, actually, use a calculator. 2.54 times 15 is 38.1, approximately. So now that everything is in centimeters, I can see if this simplifies to 1 centimeter over 5 meters. Actually, that's not even in meters. Okay. So now I have to change the bottom in meters. So, which would be, this is, oh my God. I refuse to believe. So, 0, let me take this, 7.62 centimeters, that's okay. 38.1 centimeters, not even 1 meter. Okay, it's 0.381 of a meter. Now, if you look at this, in the original scale, we want to use is 3 centimeters to 15 meters, which are simplified to 1 centimeter to 5 meters. There is no way, right, that 7 centimeters, right, 7 is large, it's about 4 times my height, and they're saying that 7.762 centimeters is about 0.38 from the floor to about your thigh. That's how tall not even your thigh, I'm sorry, your knees. That's 0.38 centimeters. So this makes absolutely no sense. So A, you're out. And B. Finally, centimeters to meters. So let's take a look at B. So B says 1 centimeter over 5 meters. And ding, ding, ding. This one is the same, sorry, not an X. This scale is the same thing as this scale. And we've simplified, so we know that they're the same. So that works. 3 meters to 15 centimeters. 3 meters to 15 centimeters. Doesn't even make sense. Okay, 3 meters to every 15 centimeters. 15 centimeters. And even if we change this the centimeter here, let's divide that. We write cm instead. 15 centimeters. So let's change that to 1 centimeter. I'll divide this by 15. I get 1 centimeter. And if I divide the top by 15, right? 3 divided by 15 is a very small number, 0.2. So every centimeter says is equal to 0.2 meters, which obviously is not the same as 3 centimeters to 15 meters. That's gone. What about D? 4 millimeters. So 4 millimeters. Millimeters to 2 meters. Well, can we change millimeters to centimeters? 4 millimeters is not. So remember, 10 millimeters equals 1 centimeter. So let me set up a ratio here. Remember that? King's Henry, dear brother, drinks chocolate milk. Remember changing that in whatever, 3rd grade or 4th grade? So we're going to change millimeters to centimeters. So 4 millimeters. So actually, I'm sorry. 10 millimeters equals 1 centimeter. So on the other side, we're going to write millimeters. We have the 4 millimeters. We have x centimeters, because that's what I'm trying to find out. So if I cross multiply, I get 10x equals 4. Divide that by 10, divide that by 10. Oops. And I get x is 0.4. So 4 millimeters in centimeters, God knows how many of you remember how to change that, is the same thing as 0.4 centimeters. Okay, I'm going to erase this stuff here. Over 2 meters. So the first adjustment that you had to make was change the units. Change millimeters to centimeters. Okay, and now that you have the 2 units correct, centimeters and meters, we can simplify this and see if we get 1 centimeter or 5 meters. Jeez. So, how do I get the 0.4 to look like a 1? I'm going to divide by 0.4, which means I divide the bottom by 0.4. 0.4 divided by 0.4 is 1. 2 meters divided by 0.4, guess what that is? That's 5. So this one, letter D, is actually the equivalent ratio as this one and this one. So B, D, and original are all the same, just written in different language. Then we have the last one. 1 inch is 5 feet. That doesn't even make sense. Okay. No. Please. No. 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 6. On a blueprint, a living room is 2.1 inches wide. So let me put it like this. Imagine a living room your living room, your home. It's 2 inches wide in your drawing. You do a little drawing. The blueprint has a scale of 1 inch to 10 feet. So the scale in your drawing, your notebook says I used 1 inch is 10 feet. How wide would the living room be on the blueprint that has a scale of 1 inch to 15 feet? Okay, so first of all, let's find out how wide. All right, so this is your drawing. So you, in your notebook, used the drawing, right? The width of your living room, and you drew it in your notebook, and you wrote that I'm going to use a scale of 1 inch is 10 feet. And you drew it, and here's the width of your living room, and it was 2.1 inch. So in real life, how wide is your living room? Well, you can use that scale. 1 inch, 10 feet. Your living room came out at 2.1 inches. How many feet does that equal to? Well, here's my proportion. Set it up. 1 times x is x, and 10 times 2.1 is 21 feet. So in real life, your living room is 21 feet wide. Okay. Now, the thing is, somebody else want to draw your living room, right? The wideness of your room, right? But they want to use this scale. 1 inch is 15 feet. Notice the difference between his scale, or her scale, and yours. Yours was 1 inch to 10 feet, and his or hers is 1 inch to 15 feet. Right, so is it going to be smaller, or is it going to be greater? Well, when we talk about that ratio here, when we're comparing here 1 to 15, and here's 1 to 10. So the 1 to 15, right, the difference is much bigger. So this one is going to be smaller. Let's see how it's much smaller. So using that scale, right, here's the width of your living room. How many inches would that be on his or her drawing of your living room? So x inches. Cross multiply, we got 15x equals 21. Divide by 15, divide by 15, x equals, what's 21 divided by 15? 1.4 inches. So when this person draws your living room, right, the living room that's 21 feet, but in his drawing, it became 1.4 inches, which was a little bit smaller than your drawing at 2.1 inches. There we go. Yeah, kind of double 2 steps there for you to do. Here's an unlabeled rectangle and several quadrilaterals that are labeled. Okay. In the table, smaller. Oh, no, I can't really see. In the table, mark all the quadrilaterals that are scale copies of the unlabeled rectangle. Then, for all scale copies, write the scale factor that was used to create it. Oh, jeez. Alright, so this is the original. Right, this one is the original. Let me get some measurements here. This is a 2, this is a 4. If it's a scale copy, okay, let's look at A. Well, if it's a scale copy, first of all, the shape has to be the same. It's a rectangle here. This is a parallelogram. The angles are different. So A is theta. What could B? Well, potential. Let's look at the height here. The height's 3. So 2 became 3, right? And then what's the width? 1, sorry, the width here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now let's think about it. How did a 4 become 8 times 2? So if 2 times 2 is 3, then this is a scale copy, right? Because we're using the scale factor for all the lengths, all the sides, right? So you got to multiply everything by 2. Well, 4 times 2 is 8, check. 2 times 2 is not 3. Then obviously this is not a scale copy. Okay, so now if you have a scale copy, you have to use the same scale factor and keep the same shape. So this one also C. Well, 1, 2, 3, that's a 3. This is 1, 2, 3, 4, 5, 6. Well, let's write this as a proportion. So 2, the ratio of these two sides, 2 over 4, should equal the ratio of these two sides. So remember, we have to use the same two sides, right? And the corresponding sides. So the 2 and the 3, they match. Those are corresponding sides. And the 4 here and the 6 are corresponding sides. So when you set up this way, well, you can cross multiply. 2 times 6 is 12, 3 times 4 is 12. What does that tell you about those two ratios? They're the same. So that's one way of doing it. Is there a different way of doing it? Well, you can also simplify. 2 over 4, if you simplify 2 over 4, it becomes a half. If you simplify 3 over 6, it's also a half. Are these two ratios the same? Yes, they are. So what does that tell you about the original one C? They are scale copies. And just for you to know, well, there's a third way. How did the 2 become a 3? How did the 4 become a 6? 2 times what is 3? Well, times 1.5. 4 times what is 6? Times 1.5. Did we use the same scale factor for each of the dimensions? Yes, we did. So 4, we multiply each of the sides by 1.5, and you got scale copy. So C is definitely a scale copy. I think this is a little review, right? So C. Right. How about D? Alright, so let me write a number D that looks like a 1 and this looks like a 2. So again, right, the ratio of the height here and the width, and then on this side the ratio of the height, which is 1, and the width, which is 2. Are these two ratios the same? Yes, they are. Isn't 2 and 4 the same thing as 1 over 2? Right? So how did the 2 become 1? We divided by 2. That's the second way we can look at it. How did the 4 become a 2? Divided by 2. So did we use the same scale factor? So I'm actually, let me take that back. Scale factor, in this case, is not 2, because we're multiplying. 2 times what is 1 is times half. 4 times what is 2 will be times half. So the scale factor that was used is the same. Okay, so E, am I doing E? Yeah. No, I'm doing D. D is, yes. What about E? Well, some numbers there. This is 2, and this is 4. Guess what? It's the exact same rectangle. So notice that the ratio of the two sides matches with the two corresponding sides. The ratio is a half. The ratio is a half. What was the scale factor used? How did this 2 become 2? How did this 4 become 1? The scale factor that was used was 1 to create the new image labeled rectangle. So this is definitely a scale copy. F, I'm not going to make any comments. You can definitely see that they're not even the same shape. G, that's 2, and this is 1, 2, 3, 4, 5. Are they scale copies of each other? Well, I hope you said no. So, to be a scale copy, you have to use the same scale factor. So how did this 2 become 2 times 1? Great. So which means that at the bottom, I should have used a scale factor as 1. 4 times 1, 5. It is not. So is this a scale copy? Although it's still a rectangle and it looks the same, we didn't use the same scale factor. And last one is this guy. So 1, 2, 3, 4. This is 4. This is 1, 2, 3, 4, 5, 6, 7, 8. You can obviously tell that this is scale copy. So the corresponding in two sides 2 and 4. How did the 2 grow to be a 4? The scale factor was 2. Did we use the same scale at the bottom? Multiply by 2? Yes, we did. Look, 4 times 2. Cross multiply. 8 times 2 is 16. 4 times 4 is 16. Right? So which ones are we saying was good? C, D, E, and H. What was the scale factor for C? It was 1.5, right? Scale factor for D was a half. We multiply everything by half. For E, this one, the scale factor was 1 because it resulted in the same exact copy. Remember, if it's greater than 1, it's going to be bigger. If it's equal to 1, it's going to be the same. If it's less than 1, like a half, it's going to be smaller. And H was multiplied by 2, and it got bigger. Is that it? Yeah, that's it. So that's part one. That's the practice. Okay. So, I'll post the video right away.